Water, the source of all life, the boundary between civilization and collapse. For thousands of years, the people of China faced a paradox that would have destroyed lesser societies. Too much water in summer, drowning crops and villages beneath roaring floods. Too little water in winter and spring, watching fields crack like broken pottery. Watching children's lips bleed from thirst, watching entire communities pack their belongings and walk away from ancestral lands that could no longer sustain them. The Yellow River, called China's Sorrow, changed course 26 times in recorded history, each time erasing entire cities from existence. The Yangtze swallowed harvests with the regularity of seasons, and between these catastrophes, droughts stretched across years, turning fertile provinces into wastelands where desperate families sold their children for a handful of grain. This was the crisis that shaped Chinese civilization, the razor's edge between abundance and annihilation. Modern engineers, with their computers and concrete, look at satellite images of ancient China and ask a question that haunts them. How did these people not only survive, but thrive? The answer lies buried beneath centuries of silt and collective forgetting. 9 water systems, each a masterpiece of engineering that solved the unsolvable, each now lost to time, their lessons abandoned in humanity's rush toward modernity. These were not simple ditches or primitive dams. These were sophisticated hydraulic networks that managed water with a subtlety that modern technology struggles to replicate. They prevented floods without blocking rivers. They stored water without creating the ecological disasters that plague contemporary reservoirs. They turned China's most vulnerable regions into its most productive heartlands. And then, slowly, deliberately, we forgot them. Some were buried by the same rivers they once controlled. Some were abandoned when political centers shifted and the knowledge keepers died without passing on their secrets. Some were deliberately destroyed, deemed backwards relics by modernizers who believed the future had no use for the wisdom of the past. But the droughts have returned. The floods continue. And in engineering departments across China and around the world, researchers are rediscovering these lost systems with a mixture of awe and regret, realizing that the ancestors solved problems we are still struggling to address. The first of these lost systems emerged 51 centuries ago in the Yangtze River Delta, where the ancient city of Liangzhu faced the primordial challenge that would define Chinese civilization. The region was a death trap, a low-lying floodplain where summer monsoons transformed the landscape into an inland sea, destroying rice crops with predictable cruelty. Most ancient peoples would have moved to higher ground, abandoning the fertile delta for safer territory. But the Liangzhu culture chose defiance over retreat. They chose engineering over exodus. Over decades, perhaps centuries, they constructed what archaeologists now recognize as the oldest formalized water management system in human history. A hydraulic network spanning nearly 100 square kilometers that rewrote the rules of what pre-industrial societies could achieve. The scale alone challenges everything we thought we knew about ancient capabilities. The system consisted of 11 earthen dams, the largest stretching 900 meters long and requiring the movement of 283,000 cubic meters of earth. No draft animals pulled the loads. No wheeled carts hauled the material. Archaeological evidence shows that every handful of soil, every stone, every reed was moved by human hands and transported by boat through a network of specially constructed canals. Researchers calculate that building just one of the larger dams required 3,000 laborers working continuously for 8 years. 8 years of digging yellowish clay from nearby hills, of dredging grayish clay from river channels, of constructing bamboo baskets, and wooden frames, of coordinating thousands of workers without modern communication, without machinery, without any of the tools we consider essential for large-scale construction. The purpose was dual, addressing both halves of the water paradox that threatened survival. During the monsoon season, a sophisticated system of levees, gates, and channels diverted excess water away from agricultural areas and living spaces, preventing the catastrophic flooding that had previously made permanent settlement nearly impossible. But the true genius revealed itself during the dry season. The massive reservoirs created by the dam system stored rainwater from the wet months. then released it through carefully controlled channels to irrigate rice paddies when natural rainfall disappeared. This wasn't just flood control or irrigation, it was comprehensive water management that worked with the natural hydrology of the region rather than against it, a principle that modern dam builders have systematically ignored, usually to catastrophic effect. The Liangzhu system enabled the development of a sophisticated urban civilization in a place where nature had previously forbidden such development. The city that grew within this protective hydraulic embrace became one of the great centers of ancient China, with specialized craftspeople, social stratification, monumental architecture, and a rice-based agricultural surplus that freed significant portions of the population from food production. Then, approximately 43 centuries ago, it all ended. The city was abandoned. The hydraulic system fell into disrepair. Archaeological evidence suggests that a catastrophic flood, larger than anything the system was designed to handle, may have overwhelmed the defenses and broken the confidence that had sustained the community for generations. Or perhaps the social organization required to maintain such an elaborate system collapsed for internal reasons, and once the maintenance ceased, the carefully balanced network degraded rapidly. Whatever the cause, the knowledge disappeared. For 4,000 years, the system lay buried beneath river silt and agricultural fields, its existence unknown until archaeologists from University College London and Chinese institutions spent 4 years excavating and surveying the site in the 21st century. The rediscovery sent shockwaves through the archaeological community because it pushed back the date of formalized hydraulic engineering in China by more than a millennium and demonstrated organizational capabilities far beyond what scholars had attributed to cultures of that era. What the Liangzhu system proved in theory, the engineers of the Qin dynasty perfected in practice 2,000 years later, creating not just a solution to the water crisis, but a transformation so complete that it changed the political destiny of an empire. In the year 256 BC, the Chengdu Plain faced the same paradox that had plagued the Yangtze Delta millennia earlier: devastating floods alternating with crippling droughts, a landscape rich in potential but hostile to stable civilization. The Min River descended from the Tibetan plateau with terrifying force, carrying glacial meltwater and mountain runoff that could strip topsoil from fields in hours. Then, as the seasonal flows decreased, the same river would retreat, leaving the plain parched and unproductive. The king of Qin commissioned Li Bing, a governor with revolutionary ideas about water management, to solve the crisis. What Li Bing created at Dujiangyan was not merely a solution but a complete reimagining of how humans could interact with rivers. A system so advanced that it operates perfectly to this day, 22 centuries later. Without pumps, without concrete, without any of the technologies we consider essential for modern water management. The brilliance began with rejection. Li Bing rejected the conventional wisdom that controlling rivers meant building dams. He understood what modern engineers regularly forget. Dams block water, creating artificial lakes that drown ecosystems, trap sediment that should fertilize downstream fields, and eventually fail catastrophically when floods exceed their design capacity. Instead, Li Bing chose to work with the river's nature, creating a system that divided, directed, and balanced water flow without ever trying to stop it entirely. The first component, called the fish-mouth levee because of its distinctive shape, splits the Min River into 2 channels: an inner channel that carries water toward the Chengdu Plain, and an outer channel that allows excess water to continue its natural course downstream. The shape is not arbitrary. The pointed levee functions like an airplane wing in water, using fluid dynamics principles that wouldn't be formally described by European scientists for another 2,000 years. During flood seasons, the outer channel automatically carries away 60% of the flow and 40% of the sediment. During dry seasons, the proportions reverse, sending more water into the irrigation channel when it's needed most. But dividing the water solved only half the problem. Li Bing also needed to control sediment, the fine particles of mountain soil that could clog irrigation channels and turn his system into an expensive, useless monument within a generation. The second component, the flying sand weir, addressed this challenge with elegant simplicity. Built at a carefully calculated height, This low spillway allows water to flow over it during high flow periods. But the curved shape creates a vortex that lifts sediment particles and carries them over the weir into the outer channel where they flow harmlessly downstream. The system is self-cleaning, requiring no mechanical dredging, no elaborate maintenance, just the natural physics of flowing water, removing what would otherwise become a fatal accumulation. The third component solved the final challenge: how to deliver water from the higher elevation river to the lower elevation agricultural fields without creating catastrophic flooding. The Biopingku, or bottleneck channel, is a narrow passage cut through Mount Yuli, restricting flow to exactly the volume that the irrigation channels can handle safely. When water levels rise above the channel's capacity, the excess automatically spills over the flying sand weir before it can cause flooding in the irrigation system. When water levels drop, the bottleneck ensures that available water is concentrated rather than spread too thin to be useful. These three components work together in a carefully balanced system that requires no external power, no moving parts, no computer controls. The system regulates itself through pure hydraulic physics, responding automatically to changing conditions without human intervention. Modern hydrologists studying Dujiangyan describe it with a mixture of admiration and frustration, because it accomplishes what contemporary dam projects costing billions of dollars consistently fail to achieve: comprehensive flood control, reliable irrigation, minimal environmental impact and operational sustainability measured not in decades but in millennia. The results transformed Chinese history in ways that resonate across centuries. Before Dujiangyan, the Chengdu Plain was a marginal region, productive in good years, but vulnerable to the extremes that made long-term planning impossible. After Dujiangyan, the plain became known as the Land of Abundance, producing massive rice harvests with predictable regularity. The agricultural surplus funded the Qin military expansion that unified China for the first time, ending centuries of warring states and creating the template for Chinese civilization that persists to the present day. The Qin dynasty collapsed, but Dujiangyan endured. The Han dynasty maintained it. The Tang dynasty expanded it. The Song, Yuan, and Ming dynasties all recognized its value and invested in its preservation. Each generation added refinements, but the core system designed by Li Bing 22 centuries ago remains functionally identical to the structure working today. In the 21st century, Dujiangyan irrigates 668,700 hectares of farmland, providing water security for millions of people and generating billions of dollars in agricultural value annually. Yet the system was nearly lost, not to floods or earthquakes, but to the same modernization impulse that has destroyed so many traditional technologies. In the mid-20th century, Chinese engineers trained in Soviet methodology proposed replacing Dujiangyan with a modern concrete dam, arguing that ancient systems were inherently inferior to contemporary designs. Fortunately, historical research and hydraulic analysis convinced decision-makers that the ancient system was not just functional, but superior to the proposed replacement in almost every meaningful metric: cost, sustainability, environmental impact, and long-term reliability. UNESCO designated Dujiangyan a World Heritage Site in the year 2000, recognizing it as an irreplaceable masterpiece of human ingenuity, but the recognition came with a troubling realization. Dujiangyan survived because it remained in continuous use, maintained by communities that understood its value, but it was the exception, not the rule. Across China, dozens of comparable systems had been abandoned, forgotten, or deliberately destroyed during various modernization campaigns. The knowledge embodied in these systems, refined over centuries of practical experience, was disappearing faster than it could be documented. While Dujiangyan was transforming the Chengdu Plain into an agricultural powerhouse, another engineering project was simultaneously revolutionizing a completely different landscape, 700 kilometers to the northeast, creating what would become one of the most politically significant water systems in Chinese history. The Guanzhong Plain in Shanxi province faced challenges that made the Min River look manageable by comparison. This was not a region of too much water, but a landscape of relentless aridity. where the Jing River and Luo River provided theoretically sufficient water, but at completely the wrong times and in completely the wrong places. Centuries of attempts at irrigation had failed because engineers kept trying to force water uphill through channels that quickly silted or collapsed, wasting enormous labor for minimal results. In 246 BC, the state of Qin commissioned an engineer named Zheng Guo to solve the crisis, but the project's origin story reveals the ruthless calculation that characterized ancient Chinese statecraft. According to historical records, Zheng Guo was initially sent by a rival state to sabotage Qin by convincing them to waste resources on an impossible canal project, exhausting their treasury and labor force while accomplishing nothing. The plan was sophisticated political warfare, recognizing that massive infrastructure projects could bankrupt kingdoms as effectively as military defeat. But Zheng Guo, upon surveying the landscape, realized that the project was not only possible, but transformative, and he committed himself to its success even after his original sabotage mission was discovered. The Zhengguo Canal, as it came to be known, stretched 150 kilometers across the Guangzhong Plain, drawing water from the Jing River at a carefully selected elevation that allowed gravity to carry water across the entire region without requiring pumps or elaborate lifting mechanisms. The engineering challenge was extraordinary because the canal had to maintain a precise gradient across its entire length, dropping exactly enough to keep water flowing, but not so much that the current would erode the earthen channel. Modern surveying with laser levels and GPS struggles to achieve this precision across such distances. Zheng Guo accomplished it using wooden frames, water levels, and mathematical calculations that would not be formally codified for centuries. The construction process required innovations that became standard practice for Chinese hydraulic engineering. Workers discovered that mixing lime with local clay created a water-resistant material that prevented seepage and erosion, essentially inventing a primitive form of hydraulic cement that anticipated European developments by 2 millennia. They developed a bamboo pipe system for crossing valleys, creating what were effectively ancient siphons that allowed water to maintain elevation without elaborate aqueducts. Most importantly, they created a network of secondary channels that distributed water with astonishing precision, ensuring that fields at the far end of the system received adequate irrigation even during low-flow periods. The transformation was immediate and overwhelming. Before the canal, the Guangzhong Plain produced approximately 300,000 shi of grain annually, barely sufficient for the local population with no surplus for trade or military supply. After the canal's completion, production increased to more than 4 million shi, a 14-fold increase that exceeded even the most optimistic projections. The desert landscape that had limited Qin expansion suddenly became an agricultural powerhouse capable of supporting massive armies and funding unprecedented military campaigns. Within a generation, Qin conquered all rival states and unified China for the first time in history, creating the Qin dynasty that gave China its name. Historians still debate whether this unification would have been possible without the agricultural revolution enabled by the Zhengguo Canal. For 2,000 years, the canal continued operating, serving the Han, Tang, and subsequent dynasties. Each generation modified and expanded the system, but the core channel laid out by Zheng Guo remained the foundation. At its peak during the Tang dynasty, the canal irrigated 400,000 hectares of farmland and sustained the prosperity that made Chang'an, modern Xi'an, the largest and wealthiest city in the world. Then, gradually, the system declined. Not from a single catastrophe, but from accumulated neglect, each generation maintaining it slightly less carefully than the previous, each dynasty focusing resources on newer projects while taking the ancient canal for granted. By the 20th century, significant portions had silted completely, rendered useless by the same sediment accumulation that Li Bing's Dujiangyan system had been specifically designed to prevent. Modern restoration efforts have revived portions of the canal, but much of the original engineering knowledge has been permanently lost. Contemporary engineers can restore the channel, but struggle to replicate the precise gradient calculations and water distribution networks that made the original system so effective. The lesson resonates across millennia. Even the most brilliant engineering becomes useless if each generation fails to understand and maintain what they inherited. While the Zhengguo Canal was conquering drought through scale and precision, another system was solving a completely different problem through innovation so radical that modern engineers initially refused to believe the historical records could be accurate. In 214 BC, the Qin dynasty faced a military logistics nightmare that threatened to derail their expansion into southern China. The empire needed to supply armies operating in what is now Guangxi province, but the geography was absolutely hostile to conventional supply lines. Mountain ranges blocked overland routes, making transport slow, expensive, and vulnerable to ambush. The river systems flowed in the wrong directions, with the Xiang River flowing north toward the Yangtze and the Li River flowing south toward the Pearl River Delta. Supplying southern armies required transporting goods hundreds of kilometers upstream, then carrying them overland across mountain passes, then loading them onto different boats for the downstream journey, a process so inefficient that grain often rotted before reaching its destination. The emperor assigned General Shi Lu to solve the problem, expecting him to build roads or perhaps construct a series of fortified supply depots. Instead, Shi Lu proposed something unprecedented, connecting two river systems that flowed in opposite directions by cutting a canal across the watershed divide. The concept was theoretically possible, but practically insane. The watershed divide at Xing'an in Guangxi province rises 34 meters above the surrounding river valleys, meaning any canal would need to climb a mountain, cross the peak, then descend the other side while maintaining enough water flow to float loaded transport barges. The solution Shi Lu engineered anticipated technologies that European canal builders would not develop for 1,500 years. The Lingkou Canal, also called the Magic Canal because contemporary observers could not understand how it worked, was only 34 kilometers long but incorporated innovations that revolutionized hydraulic engineering. First, Shi Lu constructed a dam across the Xiang River that diverted 70% of the flow into an artificial channel while allowing the remaining 30% to continue the river's natural course. The diverted water flowed into a carefully graded canal that climbed gradually toward the watershed divide, using a series of switchbacks that minimized the gradient at any single point. But the revolutionary innovation came at the divide itself, where Shi Lu installed a series of flashlock gates that could be closed to raise water levels in specific sections of the canal, allowing boats to float over obstacles that would otherwise be impassable. This was the first practical implementation of pound locks, the technology that would eventually enable the Panama Canal and every other major elevation change canal in the world. Shi Lu's design was simpler than modern locks, using single gates rather than the double gate chambers that became standard practice, but the principle was identical. Create enclosed sections that can be filled or drained independently to raise or lower boats to different elevations. Contemporary Chinese engineers described watching boats being carried uphill by water, a sight so counterintuitive that many officials accused Shi Lu of sorcery. The military impact was immediate. Supply ships could now travel continuously from the Yangtze River system to the Pearl River system, cutting transport time by 70% and reducing costs even more dramatically because goods no longer needed to be loaded and unloaded multiple times. The Qin conquest of southern China, which had stalled repeatedly due to supply failures, succeeded within 3 years of the canal's completion. But the canal's importance extended far beyond military logistics. For 2,000 years, the Lingkou Canal served as a critical commercial artery connecting northern and southern China, facilitating trade in rice, tea, silk, porcelain, and countless other goods. Cities along the canal grew wealthy from transport fees and trading opportunities. Technological innovations spread faster because ideas could travel the same routes as goods. The canal literally connected two civilizations that geography had separated, creating a unified Chinese cultural and economic space that persists to the present day. The engineering sophistication becomes even more impressive upon detailed examination. The canal maintained precise water levels despite significant seasonal variation in the Xiang River's flow, using overflow spillways and adjustable gates that automatically balanced the system. The channel bottom was lined with stone to prevent erosion. With each stone cut and fitted with precision, that modern masons admire. The banks were reinforced with a sophisticated layering system that combined earth, stone, and vegetation to prevent collapse during floods. Modern hydrologists studying the Link Canal describe it as functionally equivalent to 19th century European canals, except that it was built in the 3rd century BC with hand tools and animal labor. UNESCO is currently considering it for World Heritage status, recognizing it as a technological achievement that fundamentally shaped Asian history. Yet, like so many ancient systems, the Linku Canal nearly disappeared during the 20th century. Portions were abandoned when rail lines offered faster transport. Sections were damaged during various conflicts and never properly repaired. The lock system, which required specialized knowledge to operate and maintain, stopped functioning when the last generation of trained operators died without passing on their expertise. By the 1980s, significant portions of the canal were dry, clogged with sediment, or had been built over by expanding towns. Recent restoration efforts have revived the canal as a tourist attraction and cultural monument, but its functional purpose as a transport artery is essentially finished, replaced by highways and railways that move goods faster, but lack the elegance and sustainability that characterized the original system. The restoration process has been humbling for modern engineers who have discovered that they cannot simply rebuild what existed. The original lock gates were made from a specific type of wood that is now rare. The stone used for channel lining came from quarries that closed centuries ago. Most critically, the precise hydraulic calculations that balanced water flow throughout the system were never written down, transmitted instead through apprenticeship from one generation of canal operators to the next. When that transmission broke, the knowledge vanished, leaving contemporary engineers to reverse engineer a system they can observe but cannot fully replicate. The pattern repeating across these first 4 systems reveals a troubling truth that would define water management throughout Chinese history. Brilliant engineering solutions followed by gradual knowledge loss, not because the systems failed, but because society stopped valuing the wisdom embedded in their own infrastructure. The 5th system demonstrates this pattern with particular tragedy because it was designed not just to manage water, but to reshape an entire ecosystem, and its loss triggered environmental collapse that continues to the present day. The Yellow River Plain in Henan Province faced a unique crisis that combined all the worst elements of Chinese water challenges into a single catastrophic package. The Yellow River carried more sediment than any other river on Earth, earning its name from the yellowish-brown color created by millions of tons of loess soil washed from the highlands. This sediment constantly raised the riverbed, causing the channel to shift unpredictably and catastrophically, sometimes moving hundreds of kilometers in a single flood event, and drowning entire provinces beneath turbulent water. Between 602 BC and 1938 AD, the Yellow River changed course 26 times, each shift creating refugees by the millions and destroying agricultural infrastructure that had taken generations to build. But the sediment that made the river so dangerous also made it invaluable, because those same particles that clogged channels and caused floods also created the richest agricultural soil in China when properly managed. The challenge was capturing the benefit while avoiding the catastrophe, transforming sediment from destroyer to creator. During the Han Dynasty, around 132 AD, engineers developed a system called the Hongze Wetland Management Complex, a sophisticated network that used natural lake systems as settling basins to capture sediment while allowing cleaner water to flow into irrigation channels. The concept was revolutionary because it recognized that fighting the sediment was futile, that the only sustainable approach was working with the river's nature rather than against it. The system centered on Lake Hongze, a natural depression that engineers expanded and formalized into a massive settling basin. During high-flow periods, water entered the lake through carefully positioned inlets that slowed the current, causing sediment to settle to the bottom, while clearer water flowed out through outlets positioned higher on the lake's edges. The accumulated sediment was periodically dredged and spread on agricultural fields as fertilizer, turning the river's curse into its blessing. But the brilliance extended beyond simple sedimentation. The engineers created a multi-stage system of interconnected lakes and wetlands, each serving specific functions in the water management network. Some lakes captured coarse sediment first, protecting downstream infrastructure from the largest particles. Others served as reserve storage during droughts, their water levels carefully managed through a system of gates and channels that distributed water according to agricultural need rather than natural flow patterns. Still others functioned as fish farming operations, creating protein sources that supplemented the region's diet, while also providing economic incentives for communities to maintain the water quality and infrastructure. The ecological sophistication rivals modern conservation areas that claim to integrate human use with environmental protection. The wetlands supported massive bird populations, including migratory species that traveled from Siberia to Southeast Asia, using the area as a critical rest and feeding stop. The diverse aquatic vegetation filtered water naturally, removing impurities that would otherwise accumulate downstream. The interconnected water bodies moderated local climate, reducing temperature extremes and increasing humidity, in ways that benefited surrounding agriculture. For more than 1,000 years, the system functioned with remarkable stability, supporting one of the highest population densities in pre-modern China while maintaining ecological health that contemporary records describe in terms approaching reverence. Poets wrote about the abundance of fish and waterfowl. Agricultural records document consistently high yields. Tax records show steady revenue collection, indicating economic stability built on agricultural reliability. Then came the catastrophic decision that modern environmental scientists regard as one of history's greatest ecological disasters, though it was made with the best intentions and the certainty of progress. In the 1950s, Chinese engineers trained in Soviet heavy industry methodology looked at the Hongzhe system and saw backwardness, inefficiency, and wasted potential. The wetlands could be drained for agriculture, the lakes could be dammed for hydroelectric power, the sediment could be controlled with modern concrete structures rather than primitive settling basins. Most critically, the engineers believed that scientific central planning could optimize water flow in ways that traditional systems, developed through trial and error over centuries, could never achieve. The transformation was rapid and comprehensive. Wetlands were drained and converted to crop fields. Natural lake edges were replaced with concrete embankments. The complex network of channels and gates was simplified into a more direct system that prioritized fast water movement over careful sediment management. For a few years, the changes seemed successful. Crop production increased in the newly drained fields. The simplified system required less maintenance labor. Everything appeared to validate the modernization approach, but within a decade, the consequences became undeniable. Without the settling basins, sediment accumulated rapidly in irrigation channels, requiring constant dredging that was far more expensive than the maintenance the original system had required. The simplified hydrology eliminated the buffer capacity that had protected against both floods and droughts, making the region more vulnerable to climate variability rather than less. The loss of wetland habitat triggered cascading ecological collapse, with bird populations crashing, fish stocks disappearing, and water quality degrading to levels that required expensive treatment before the water could be used for irrigation or drinking. Most devastatingly, the removal of natural flood absorption capacity meant that stormwater now moved faster and hit harder downstream, turning floods that the original system would have moderated into catastrophic disasters. By the 1990s, government assessments acknowledged that the modernization had been a comprehensive failure, destroying a sustainable system and replacing it with infrastructure that was simultaneously more expensive to maintain and less effective at its intended purpose. Restoration efforts have been ongoing for 3 decades, attempting to reconstruct wetlands and restore natural hydrology, but the original system's complexity makes full restoration nearly impossible. The engineers can rebuild lakes and channels, but the subtle gradients, the precise gate positions, the intricate timing of water releases that made the original system work were never formally documented. That knowledge lived in the experience of the water managers who operated the system, transmitted through apprenticeship and refined through generations of observation. When those practitioners were dismissed as obsolete and the system was dismantled, that accumulated wisdom vanished, leaving contemporary engineers with archaeological evidence and historical descriptions, but no practical manual for operation. While the Yellow River system was managing sediment through ecological integration, another region was solving the opposite problem with equal sophistication: how to sustain agriculture in areas with almost no surface water at all. The Tarim Basin in Xinjiang province presents one of the most extreme environments humans have ever tried to civilize. An arid depression surrounded by mountains where annual rainfall measures in single-digit centimeters and summer temperatures regularly exceed 45 degrees Celsius. No rivers flow year-round through most of the basin. No lakes provide ready water sources. The landscape is dominated by the Taklamakan Desert, whose name translates as "you go in and you don't come out," a place where exposed water evaporates almost instantly and surface irrigation is physically impossible. Yet for 2,000 years, this apparently uninhabitable desert supported thriving cities, productive agriculture, and the famous Silk Road trade routes that connected China with Central Asia and beyond. The solution was the Carrez system, one of humanity's most ingenious water management technologies, and one that has almost completely disappeared from use despite its extraordinary effectiveness. The Carrez system, called Qanat in Persian and Qanat in Arabic, originated in ancient Persia around 3,000 years ago and spread along trade routes to reach Xinjiang approximately 2,000 years ago. The basic principle sounds simple, but the execution required engineering knowledge that still impresses modern hydrologists. Instead of bringing water across the surface where it would evaporate, bring it underground, where temperature and air exposure are minimized. The construction began in the foothills, where seasonal snowmelt from the surrounding mountains seeped into underground aquifers, creating subterranean water sources that remained liquid year-round, despite surface conditions that would freeze water in winter and evaporate it in summer. Engineers identified these aquifers through techniques that combined geology, hydrology, and what can only be described as intuition, developed through generations of experience. Once an aquifer was located, workers hand-dug a gently sloping tunnel from the aquifer source toward the agricultural fields that needed water, maintaining a gradient precise enough to keep water flowing through gravity alone, but gentle enough to prevent erosion that would collapse the tunnel. This is where the engineering becomes extraordinary. A single Carrez tunnel typically ran between 5 and 20 kilometers, descending from aquifer to destination at a grade of approximately 1 to 3 meters per kilometer. The tunnel was barely large enough for a person to crawl through, dug entirely by hand with simple tools, requiring workers to operate in darkness, in confined spaces, breathing air that was often oxygen depleted. To enable construction and maintenance, vertical access shafts were dug every 20 to 30 meters along the tunnel's length, creating the characteristic line of holes across the desert landscape that marked Carrez locations. Each shaft required careful engineering to prevent collapse while allowing ventilation and access. At its peak in the 19th century, Xinjiang contained more than 1,700 Carrez systems, with a combined tunnel length exceeding 5,000 kilometers, representing one of the largest underground construction projects in human history, achieved without mechanized equipment. The water that emerged from Carrez tunnels was cold, clean, and flowing at rates that could irrigate significant agricultural areas. Villages grew around Carrez outlets, their locations dictated by water availability rather than surface geography. The stable water supply enabled cultivation of grapes, melons, wheat, and cotton in the heart of one of Earth's driest deserts. The underground transport meant that water loss to evaporation was reduced by 90% compared to surface channels, a critical advantage in an environment where every drop mattered. The system was sustainable in ways that contemporary groundwater extraction consistently fails to achieve, because the Carrez drew only what the aquifer naturally recharged, maintaining equilibrium between extraction and replenishment. But the Carrez system demanded constant skilled maintenance that tested community commitment and organizational capacity. Sand would gradually infiltrate tunnels, requiring periodic clearing that involved crawling through kilometers of confined darkness to dig out accumulated sediment. Earthquakes, surprisingly common in the tectonically active region, could collapse tunnel sections that then needed to be re-excavated and reinforced. Most critically, The system required communities to maintain collective organization across generations, because the benefits of a carrés served everyone in the village, while the maintenance burden fell on whoever was assigned or volunteered. This created a sophisticated system of water rights, labor obligations, and community governance that anthropologists have studied as an example of successful common resource management. The decline of the carrés system accelerated in the 20th century as modern alternatives appeared to offer easier solutions to the region's water challenges. Electric pumps made deep wells practical, allowing communities to extract groundwater without maintaining elaborate tunnel systems. Surface irrigation using pumped water seemed more flexible and required less specialized knowledge to operate. Most compellingly, the economic calculation shifted as younger generations moved to cities for education and employment, leaving fewer people available for the labor-intensive maintenance that carrés required. One by one, carrés systems fell into disrepair, their tunnels collapsing or clogging with sediment as the knowledge and commitment required to maintain them disappeared. By 2010, only about 600 carrés remained operational, less than one-third of the historical peak, and that number continues to decline despite government preservation efforts. The tragedy of losing functional carrés systems reveals a pattern that extends beyond individual technologies to touch something deeper about how civilizations value inherited knowledge versus novel innovation. This tension reached its most dramatic expression in systems that were not just engineering achievements, but philosophical statements about humanity's relationship with nature, systems designed not to conquer water, but to dance with it. The seventh lost system embodied this philosophy with particular elegance, transforming what appeared to be a catastrophic natural feature into the foundation of agricultural abundance. The Sichuan Basin, despite being one of China's most productive agricultural regions today, historically faced a water management challenge that defied conventional solutions. The region receives abundant rainfall, more than 150 centimeters annually, but the precipitation arrives in concentrated bursts during the monsoon season, creating floods that could destroy entire harvests in a single afternoon, followed by extended dry periods when crops withered for lack of water. The mountainous terrain meant that building large storage reservoirs was prohibitively expensive and geologically risky, while the porous limestone bedrock characteristic of the region meant that surface water storage often drained away through underground channels before it could be used. The solution developed during the Tang dynasty around 820 AD was the Sichuan Pond and Weir system, a distributed network that rejected the imperial scale of projects like Dujiangyan in favor of thousands of small interventions that worked collectively to transform the region's hydrology. Instead of trying to control major rivers, engineers focused on capturing and storing water at the smallest practical scale, creating an estimated 40,000 individual ponds, each serving a few families or a single village connected by a network of channels and weirs that allowed water to flow between storage units according to need and availability. The genius lay in the distribution. Each pond was sized to capture runoff from a specific micro-watershed, positioned to intercept water flowing down hillsides before it could concentrate into erosive streams. The ponds were connected in series, with overflow from higher ponds feeding into lower ones through carefully graded channels, creating a cascade system that moderated flow rates while allowing flexibility in water allocation. During heavy rains, the network absorbed water like a sponge, with each pond filling to capacity before overflow moved to the next level. During droughts, farmers could release water from upstream ponds to irrigate downstream fields, with community councils mediating disputes and ensuring equitable distribution according to long-established customs that balance need, tradition, and agricultural cycles. The environmental benefits extended far beyond irrigation. The distributed storage dramatically reduced soil erosion by capturing runoff before it could gain erosive velocity. The ponds provided habitat for fish, frogs, and aquatic insects that controlled agricultural pests naturally, reducing crop losses without requiring the pesticides that would not be invented for another millennium. The still water surfaces moderated local temperatures through evaporative cooling, creating microclimates that extended growing seasons and reduced crop stress during heat waves. Most remarkably, the system was almost entirely self-maintaining because silted ponds reduced storage capacity and therefore provided direct incentive for local farmers to dredge and maintain their portion of the network without requiring central authority to enforce maintenance schedules. For more than 8 centuries, this system sustained Sichuan's reputation as the land of abundance, supporting population densities that exceeded most of China despite the region's challenging topography and climate. The cultural impact was equally profound, creating a landscape that poets and artists celebrated as an idealized harmony between human activity and natural processes where agriculture enhanced rather than diminished ecological health. Then came the 20th century's obsession with scale and efficiency, the belief that bigger was always better, and that centralized systems were inherently superior to distributed networks. The collectivization campaigns of the 1950s looked at 40,000 individual ponds maintained by individual communities and saw inefficiency, backwardness, and wasted potential. The ponds were small, scattered, and required continuous local maintenance. Modern reservoirs could be larger, centralized, and maintained by professional engineers rather than farmers. The economic calculation seemed obvious. Consolidate the distributed system into a smaller number of large reservoirs that could be managed efficiently by specialized personnel. The consolidation was rapid and comprehensive. Thousands of small ponds were abandoned or filled in, their maintenance deemed an inefficient use of labor that could be better deployed in industrial production. The water management function was transferred to large reservoirs built in mountain valleys, impressive concrete structures that could store volumes far exceeding any individual traditional pond. For a few years, the transition seemed successful, with the new reservoirs providing reliable water supply without requiring the distributed labor that had maintained the pond system. But the consequences accumulated steadily. Without the distributed storage network, rainfall now ran off directly into streams and rivers, increasing flood severity downstream and reducing the gradual groundwater recharge that had sustained springs and wells during dry seasons. The loss of tens of thousands of small ponds eliminated massive amounts of aquatic habitat, triggering ecological changes that rippled through the food web. Most critically, the centralized reservoirs proved far more vulnerable to both floods and droughts than the distributed system they replaced, because a single reservoir could only be full or empty, providing no flexibility to respond to local variations in rainfall or agricultural need. The distributed network, by contrast, had provided resilience through redundancy, with thousands of small storage units ensuring that local shortages never became regional catastrophes. By the 1990s, agricultural productivity in areas that had abandoned the pond system was declining despite increased fertilizer use and modern irrigation technology. Government studies eventually acknowledged what farmers had known for decades. The traditional system had been more effective, more resilient, and more sustainable than the modern replacement. Restoration efforts began in the early 2000s, with government funding to reconstruct traditional ponds and revive the maintenance customs that had sustained them, but the process has been slow and incomplete. Young people who might have learned pond management from their grandparents now work in cities, and the knowledge of how to site, construct, and maintain the ponds according to traditional principles has largely vanished. Engineers can build new ponds, but without the accumulated local knowledge of micro-watershed hydrology and community water management, the reconstructed systems function less effectively than their historical predecessors. While Sichuan was perfecting distributed water storage, another region was solving an even more extreme challenge through a system so unusual that modern engineers initially dismissed historical accounts as exaggerated folklore. The Loess Plateau in Shaanxi and Shanxi provinces presents one of Earth's most difficult agricultural environments, a landscape of wind-blown silt deposits that can be hundreds of meters deep, easily eroded, and naturally almost devoid of surface water. Rainfall is sparse and highly seasonal, arriving primarily during summer thunderstorms that turn the fine Loess soil into slurry that flows like liquid, carving gullies dozens of meters deep in a single storm. The region had supported sparse nomadic populations for millennia, but permanent agriculture seemed impossible because any attempt to farm the slopes accelerated erosion while the few flat areas received insufficient water. During the Ming Dynasty, around 1520 AD, engineers developed the Yaodong water harvesting system, an approach so counterintuitive that it reversed almost every assumption about water management. Instead of trying to bring water to crops, the system brought crops to water by constructing underground farms inside cave dwellings, carved into the Loess hillsides. The caves, called Yaodong, served simultaneously as housing, storage, and controlled environment agriculture spaces, while the hillside surfaces above were engineered to harvest every drop of rainfall and channel it to underground cisterns that provided year-round water supply. The engineering began with understanding the unique properties of loess soil, which is structurally stable when dry, but collapses into mud when saturated. By carving caves into hillsides, at depths where seasonal moisture variation was minimal, architects created spaces with remarkably stable temperatures and humidity levels, remaining cool in summer and warm in winter without heating or cooling. The cave ceilings were high enough for comfortable habitation and agricultural work, with ventilation shafts providing air circulation that prevented moisture buildup and carbon dioxide accumulation. But the revolutionary innovation was the surface treatment above each cave complex. Engineers sculpted the hillside into a series of shallow basins and channels that captured rainfall and directed it into filtering systems that removed sediment before allowing water to flow into underground cisterns carved into the loess bedrock. The surface was then sealed with a mixture of clay, lime, and plant fibers that prevented erosion while maintaining enough permeability to allow water infiltration at controlled rates. The result was a water harvesting surface that could capture and store up to 80% of annual rainfall, compared to less than 20% for natural low slopes, where most precipitation either evaporated or ran off before it could infiltrate. Inside the cave complexes, families cultivated vegetables and grains in raised beds, using the stored water and the naturally stable environment. The cool temperatures and controlled humidity meant that crops required less water than surface agriculture, while producing comparable or superior yields. The caves also provided storage for harvests that remained cool and dry year-round, reducing spoilage and extending food security through seasons when surface agriculture would have been impossible. At its peak during the Qing dynasty, the system supported hundreds of thousands of people across the Loess Plateau, transforming a region previously considered uninhabitable into productive agricultural land. The cultural adaptation was equally remarkable, with entire villages existing primarily underground, their surface presence marked only by the distinctive arched entrances and the sculpted hillsides that harvested water with artistic as well as functional sophistication. The decline began in the 20th century as modernization brought different aspirations and possibilities. Underground living was reframed as backwards and primitive, associated with poverty rather than sophisticated environmental adaptation. Modern building materials made surface construction feasible even in unstable Loess soil. Most critically, electric pumps and deep drilling made groundwater accessible, apparently eliminating the need for elaborate water harvesting systems. Families began moving out of Yaodong caves into surface houses, abandoning the underground farms and allowing the water harvesting surfaces to erode back into natural, unproductive slopes. By the 1990s, less than 10% of historical Yaodong complexes remained inhabited, and almost none continued to function as the integrated water harvesting and agricultural systems they had been designed to be. The consequences for the Loess Plateau were severe, contributing to the region becoming one of China's most environmentally degraded and economically depressed areas, suffering from extreme erosion, water scarcity, and agricultural failure that has driven massive rural to urban migration. Recent research has revealed that the abandoned Yaodong system was not primitive but remarkably advanced, representing solutions to arid land agriculture that contemporary sustainable development projects are now trying to recreate using expensive modern materials and technologies. The underground agriculture concept has been rediscovered by vertical farming advocates as an energy-efficient approach to food production, while the water harvesting principles are being reapplied in desert reclamation projects worldwide. Yet the original system, refined through 5 centuries of practical experience, lies largely abandoned, its knowledge lost, because a generation decided that modern was inherently better than traditional, without fully understanding what they were abandoning. The pattern across these 8 lost systems reveals a disturbing truth. Each solution was not merely abandoned, but actively rejected by succeeding generations who believed progress meant discarding the past rather than building upon it. The 9th system embodies this tragedy most completely because it survived longer than any other, adapted through more dynasties than any comparable infrastructure, and then was destroyed in a single generation by planners who never bothered to understand what they were eliminating. The Grand Canal system of Jiangnan, the network of waterways south of the Yangtze River, represented the culmination of 3,000 years of accumulated hydraulic wisdom, a system so sophisticated that its full complexity was only understood after its destruction made reconstruction impossible. The region faced challenges that combined every difficulty encountered elsewhere: monsoon floods, seasonal droughts, tidal intrusions from the nearby ocean, and the need to move massive quantities of agricultural products and tax grain from productive rural areas to consumption centers in cities. The solution, developed incrementally from the Sui dynasty through the Song, Yuan, Ming, and Qing dynasties, was not a single canal but an integrated network of natural rivers, artificial channels, tidal gates, water level balancing reservoirs, and locks that functioned as a unified hydraulic organism, responding to conditions across the entire region simultaneously. The engineering sophistication becomes apparent only when examining how the system managed the seemingly incompatible requirements it faced. During summer monsoons, excess water needed to be evacuated quickly to prevent flooding, requiring channels that moved water efficiently toward the ocean. But during winter droughts, water needed to be retained and distributed carefully to maintain navigation depths and provide irrigation, requiring the exact opposite hydraulic behavior. The system accomplished both through a network of gates and weirs that could be configured differently according to seasonal needs, transforming the region's hydrology from liability to asset. The gates were not simple barriers, but precisely engineered structures that could modulate flow rates, allowing operators to balance water levels across dozens of interconnected channels simultaneously. Historical records describe gate operators who could predict water levels 3 days in advance based on upstream rainfall, tidal cycles, and seasonal patterns, adjusting gate positions with precision that modern computer models struggle to match. The system also solved one of the most challenging problems in hydraulic engineering: managing saltwater intrusion in tidal regions where ocean water can flow upstream and contaminate freshwater sources. The Jiangnan network included sophisticated tidal gates that allowed freshwater to flow out during ebb tides, while preventing saltwater from flowing in during flood tides, using one-way valve mechanisms that required no external power and minimal maintenance. These gates protected hundreds of thousands of hectares of agricultural land from salinization while simultaneously maintaining navigation channels that connected interior regions to ocean ports. The balance was so precise that historical accounts describe how farmers could taste the water in irrigation channels and know immediately if gate operators upstream had made an error in timing or positioning, because even slight mistakes would allow enough salt intrusion to affect crop growth. The cultural integration was equally remarkable. The canal network was not just infrastructure, but the foundation of an entire civilization's economic and social organization. Villages developed at strategic gate locations, their populations specializing in water management and developing extraordinary expertise, passed through family lines across generations. Markets organized around canal junctions where goods from different regions converged, creating trading centers that rivaled coastal ports in volume and diversity. The rhythm of life synchronized with water levels and seasonal flows, with festivals marking critical transitions like the spring gate openings that launched the agricultural season, or the autumn closures that prepared the system for winter. Poets wrote about the canals with reverence typically reserved for natural wonders, recognizing them as landscapes where human ingenuity and natural processes had merged into something transcending either alone. For more than 1,000 years, this system sustained the most productive and prosperous region of China, generating the agricultural surplus that funded imperial governments and the transportation network that unified diverse regions into a coherent economic unit. Then, in the span of 30 years during the mid-20th century, it was systematically dismantled and replaced with infrastructure that its designers genuinely believed would be superior in every way. The reasoning seemed compelling at the time. The traditional system was complex, requiring skilled operators and constant maintenance. Modern concrete channels could be simpler, requiring less labor and expertise. Electric pumps could move water according to engineered schedules rather than natural flows and tidal cycles. Centralized control could optimize the system using scientific planning rather than relying on the accumulated intuition of traditional operators. The transformation was comprehensive. Natural rivers were straightened and confined between concrete embankments. Artificial channels were reconstructed with uniform dimensions and gradients calculated to maximize flow velocity. The elaborate gate systems were replaced with simpler structures designed for mechanical rather than hydraulic operation. Most critically, the unified network was broken into separate segments, each managed independently according to local needs, rather than as parts of an integrated regional system. For several years, the changes appeared successful. Water moved faster through the simplified channels. The reduced maintenance requirements freed labor for other economic activities. Everything seemed to validate the modernization approach, but within 2 decades, the consequences became undeniable and catastrophic. The straightened rivers moved water so quickly that they eroded their channels, requiring constant dredging that was far more expensive than the maintenance the original system had required. The elimination of the complex gate network meant that the region lost its ability to buffer floods and droughts, experiencing both with increased severity despite having more elaborate infrastructure than ever before. The loss of tidal management led to progressive saltwater intrusion that has contaminated groundwater across coastal areas, reducing agricultural productivity and forcing communities to import drinking water. Most devastatingly, the fragmentation of the integrated network eliminated the resilience that had been its greatest strength, creating a brittle system where problems in one area could no longer be compensated by adjustments elsewhere. By the 1990s, government studies acknowledged that agricultural and economic productivity in the region had declined significantly compared to historical levels, and that water management costs had increased by orders of magnitude. The traditional system had been essentially free to operate once constructed, powered by gravity and tides, maintained by communities who benefited directly from its proper function. The replacement system required continuous pumping, constant dredging, elaborate monitoring systems, and professional management bureaucracies, consuming resources that far exceeded any efficiency gains. Restoration has been proposed repeatedly, but remains incomplete because the knowledge required to reconstruct and operate the traditional system has been lost. The engineers who understood how the integrated network functioned, how to read water conditions and adjust gates accordingly, how to predict system behavior based on complex interactions between natural and artificial hydrology, all died without successors because their expertise was dismissed as obsolete. Contemporary engineers can rebuild individual components, but cannot recreate the integrated system, because integration requires understanding relationships that were never documented in written form, transmitted instead through practical experience across generations of operators. The 9 lost water systems of China share a common trajectory. Brilliant innovation that solved seemingly impossible challenges, followed by centuries of successful operation that sustained civilization in hostile environments. Then, rapid abandonment, driven by the conviction that traditional solutions were inherently inferior to modern alternatives. Each system was destroyed not because it failed, but because succeeding generations failed to recognize its value until after the knowledge required to maintain it had vanished. The pattern repeats with troubling consistency across different regions, time periods, and specific technologies, suggesting that the problem lies not in any individual decision, but in fundamental assumptions about progress, tradition, and the relationship between human ingenuity and natural processes. The ancestors who designed these systems understood something that modernity has systematically forgotten. that the most sophisticated solutions work with nature rather than against it, that sustainability requires designing for maintenance rather than just construction, and that knowledge embedded in practice is often more valuable than knowledge codified in theory. These were not primitive technologies awaiting improvement by modern science, but mature solutions to problems that contemporary engineering still struggles to solve, despite vastly greater resources and supposedly superior understanding.